So during this last lecture, I will discuss the Cauchy problem and different techniques to study the Dirichlet Neumann operators that allow to study the Cauchy problem. Let's consider initial data, eta 0 and psi 0. There are many results that we could prove. First theorem, consider any value of the gravity, positive, negative, or 0. Okay, let's consider initial data that are analytic in the sense that the Fourier transform of the initial data are compactly supported. Then there exists a unique solution, a unique local in time solution. I'm not going to say much about the proof of this result. I'm not going to even to give a clean statement. I just want to mention that it can be proved quite easily. Let's say the water wave equation can be written in an abstract way as a system for the noun u, which is a coupled eta psi, a system, let's say, of the form dtu plus f of u is equal to 0. Then, instead of working with u, you can work with v, which is exponential of sigma of t modulus of du, where sigma of t is, let's say, sigma 0 minus some constant kt. Assuming that initially v0 is in L2, which amount to require that exponential of sigma modulus of du0 is in L2, which is clearly the case if these functions are compactly supported, we can proceed and write an evolution equation for v. It has to be rigorously justified, but anyway, of that form. Okay? You lose about the radius of analyticity, a loss in time, a classical trick. This allows you to make appear a parabolic term, a parabolic evolution equation, and provided that k is large enough, you can absorb the contribution of this term. It's enough to say, okay, it's a term of order 1, f is an operator of order 1, so it's quite easy to conclude the proof, provided that you know how to study f of u in Sobolev spaces or in analytic Sobolev spaces. Anyway, I am going to give more details about the proof of the following result. Now let's consider the stable case. The gravity is positive and any spatial dimension. For any initial data, eta 0 and psi 0 in the Sobolev space H infinity of Rd that we have already introduced, there exists a unique maximal solution eta psi, which is smooth in time, defined on some time interval I, with value in H infinity of Rd. Okay? And the third statement, still for G positive and in any dimension, consider eta 0 psi 0 or eta 0 tilde, psi 0 tilde, a couple of two functions which are both smooth and compactly supported. And we are going to consider initial data, eta 0 and psi 0, of the form epsilon times eta 0 tilde, psi 0 tilde. If epsilon is small enough, then we have global well-posedness, namely the maximal time interval is 0 plus infinity. So I don't know who proved first theorem 1. Theorem 2, the proof of theorem 2, that is local well-posedness, goes back to the work of Nalimov, Reed and Schinbrot, Walter Craig, Tani, Bill, Wu and Lovengrub, Bayer and Gunther, Sidgway Wu, Ogawa and Tani, Ambrose Masmoudi, Schneider and Wayne, Coutin and Scholar, David Lan, Zhang et Zhang, Ming et Zhang, myself with Nicolas Burke and Claude Zully, Heyman recently, Thibaut de Poisferré. Many people contributed to the proof of theorem 2, improving, for example, the regularity, first working with data small enough, then removing the smallness assumption, then considering data which are not in H infinity but with finite regularity, and then slightly improving the regularity down to some quite optimal threshold. The best result today is due to Albert A., Mihaela Infrim, and Daniel Tatarou. And to prove this well-posedness with very low regularity, they introduced and invented a lot of methods. The proof of theorem 3 has also a long history. It goes back to the work of Sidgway Wu, Germain Masmoudi-Chattah, myself and Jean-Marc Delors, Jonathan Pusateri, Hunter Ifrim and Tatarou, and many recent contributions too. For theorem 2, the proof is classical proof, as explained by Elena, Sobolev energy estimates. For theorem 3, you add plus dispersive estimate plus normal form transformation. So what I can explain is the proof of Sobolev energy estimate for this system. Starting with Sobolev estimates for the Dirichlet to Neumann operator G of eta. We have seen that G of eta is bounded from H1/2 to H minus a half in terms of the Lipschitz norm of eta. We have another similar estimate from H1 to L2. There are Sobolev energy estimates. For example, this one. There are many Sobolev energy estimates that goes back to the work of Craig, Bayer and Gunther, Sidgway Wu, David. With Nicolas Burke and Claude Zully, we prove the following results. It's in two parts. Consider a Sobolev index strictly larger than 1 plus d over 2, so that the Sobolev space is embedded into the space of functions which are Lipschitz. Then, for any index sigma in the interval 1/2 s, we have that G of eta maps H sigma to H sigma minus 1, and the operator norm is bounded in terms of the HS norm of eta. A second and more subtle estimate asserts that you can estimate the difference between two Dirichlet to Neumann operators. It's more delicate. Okay? And this will be bounded by some constant involving only the HS norm of eta 1 and eta 2. You have also the HS norm of F. And the HS minus half norm of the difference between eta 1 and eta 2. And one maybe subtle point is that here you see the difference of the two functions is not estimated into Lipschitz, which is not necessarily something intuitive. Okay, to prove such a result, just a comment. There are many places, many textbooks, many articles where people are just proving a priori estimates and still claiming to get existence and regularity. This is because sometimes people wave their hand, but they are right to do it. In the end, I just recall a classical argument, very powerful. Very powerful argument due to Schauder. Schauder proves this result. Continuation principle. Consider a family of operators L depending on some parameter T defined on some space B, which is a Banach space, with value in space V, which is a vector space. And T here is an external parameter. It has nothing to do with time. It's lambda. Assume that there exists a constant A such that for any lambda, for any U in B, you can estimate U in B by A times L lambda of U in V. This is an a priori estimate. You assume that you have a function U, and you assume that you can estimate the norm of U by the norm of L lambda U. Assume also that you know that L of 0 is surjective. Then L1 is surjective too. Okay? L0 is surjective, then L1 is surjective. So this is a very striking observation due to Schauder. At the time, it was really something new. And after proving this result, Schauder received a letter from Leray, where Leray said to Schauder, maybe in German, I don't know, that he was amazed that it is possible to prove the existence of a solution without knowing the uniqueness at the same time. So it's a new method to prove the existence of solution that surprised Leray. Leray suspected that there is much more behind, they started their collaboration, which led to the Leray-Schauder fixed point theorem, which is a milestone in elliptic equation. But it's enough to have this simple version. Okay, how do we apply this? For us, we have a domain. We have a domain. We have an operator. We flatten this domain. We flatten this domain to the price of replacing the Laplacian by a Laplacian with variable coefficient. Okay, what is the operator L lambda? L lambda, by definition, this is the operator divergence in x and z of A lambda x, lambda z, let's say, gradient of x, z. This is a family of operators depending on a parameter, external parameter lambda. When lambda is equal to 0, oh no, it's a bad choice, excuse me. That's so stupid. Okay, when lambda is equal to 0, this is a flat Laplacian. When lambda is equal to 1, this is the operator you want to study. Okay, well. So, by using this very simple Schauder continuation principle, you reduce yourself to proving a priori estimate for this elliptic equation, which is convenient because now you no longer have to worry about proving the existence of solution, as many people did apparently. You just have to prove estimates. To prove estimates, you can further simplify the problem by a second reduction, which is reduction to constant coefficient. And this is a method that I think is not due to Schauder. It's called in elliptic PD the cone freezing method. Or do you know the name? No, you don't know? You don't know the name? There is a reduction to constant coefficient argument. Maybe you probably know the argument. This is the essence of the proof of the Schauder estimate for elliptic equation with older coefficient. Of course, when S is strictly larger than 1 plus d over 2, the Sobolev space Hs is embedded into C1 alpha. So A, the matrix A, which depends on the derivative of eta, is C0 alpha. It has a modulus of continuity. In particular, you can freeze coefficient as follows. You pick a point x0, z0 in the lower half space, and you write the equation under the form okay? You write your equation divergence of A gradient V equal to 0 under this form. Divergence of this matrix with constant coefficient, you have frozen the coefficient at that point, equal to this matrix minus the original matrix. And the point is that this is constant coefficient. And here, you have something, because you know that you are order continuous, you can estimate here the norm in terms of the norm of x0, z0 minus xz to some power alpha. And this is small. This is small. So whenever you are elliptic or parabolic, under a smallness assumption, you can always reduce yourself to a constant coefficient. You put everything on the right-hand side, and you absorb. So you do that. Okay? On the right-hand side is small. This is constant coefficient. You know how to invert it, how to prove estimate. This is in textbook. So you are done. You are done up to the proof of nonlinear estimates, of course. Because you talk like Schauder only with variational solution and other spaces. It's not enough. You have to perform estimate in Sobolev space. So you have to use nonlinear estimates. One need nonlinear estimates. For example, they have been already used by Elena, but I want still to have something easy to state and prove the following simple proposition. Simple nonlinear estimates. For any s in 0, 1, whenever the space of functions which are L infinity and in HS is an algebra, and you have this estimate uv in HS dot is smaller than u in L infinity times v in HS plus u in HS, v in L infinity. And the coefficient here, the constant, is 1. Pick any function f from R to R, from R to R, such that f is Lipschitz. Then the Sobolev norm is bounded by k times the Sobolev norm of u. So they are the classical nonlinear estimates, except that it states only in dimension 1 for s between 0 and 1. And we have constants that are simple constants. And the proof is very short. It has to do with the Gagliardo way of writing the Sobolev norm, which is in turn a direct consequence of Plancherel theorem. The Plancherel theorem implies what? That you can write this, which is by definition, this is equal to some constant depending on s times the integral over r times r of this quotient, u of x minus u of x minus alpha squared divided by alpha to the 2s dx d alpha divided by alpha. How do you prove this? This is direct consequences of Plancherel formula. Why is that? Because the Fourier transform of, let's introduce the finite difference operator, delta alpha, which is equal to u of x minus u of x minus alpha. Then the Fourier transform of delta alpha u is equal to 1 minus exponential of minus I alpha psi u at of psi. Okay? And then it's a simple exercise to do that. One comment. We are very used today to manipulate or to handle Sobolev estimates using Littlewood-Paley decomposition and to define Bézos space using Littlewood-Paley decomposition. But if you look at the original paper of Bézos, that apparently nobody quoted, it quoted only 60 times in 60 years, Bézos introduces spaces using finite differences operator and not Littlewood-Paley decomposition. However, Treble is right to define his space using Littlewood-Paley decomposition, because if you look at the original paper of Littlewood and Paley, they introduced their decomposition in order to study the square function. They were interested in proving that, in studying the square function. Well, bref, this is to say that, okay, now, if you want to estimate this norm, you have to estimate the L2 norm of delta alpha u in L2. Okay? And this is trivial. You don't have an exact Leibniz rule for the finite difference operator, but almost. You can differentiate a product saying that it is either delta alpha of u times v plus tau alpha of u delta alpha v, where tau alpha of u is just the function obtained by shifting. So, of course, this proves the point 1 in one line. The proof of point 2 is even simpler because it's enough to observe that directly from the assumption that f is Lipschitz, you have this. And then, by the previous characterization of Sobolev norm in terms of Gargalo norm, you have nonlinear estimate. Okay? Now, if you want to prove more general nonlinear estimates, and in particular to prove nonlinear estimates that are convenient to prove Schauder estimate for a problem with limited regularity, it's convenient to introduce paraproducts. Okay? What is a paraproduct? Okay, so Jean-Michel Bonny introduced paradifferential operators. In France, people say that he also introduced paraproducts, but it doesn't seem fair because I think that paraproducts were introduced by. If you have any references, I am interested. Paraproducts. What is a paraproduct? It's a bilinear Fourier multiplier that were at the core of the interest of many people at the time. It's a bilinear Fourier multiplier. Okay, let's write a product of two functions a and b as a double integral. It's a quite complicated way of writing a product for sure. You just apply the Fourier inversion formula for a, the same for b, you multiply. But now you can decompose you have an integral, a double integral, you decompose it into 3 pieces. One where psi1 is negligible in size compared to psi2, a symmetric part, and a reminder. You call this TA of B. This is the symmetric expression, TB of A. And this is R. More precisely, if you want to be more precise, what do? You introduce a cutoff function. Let's say it's a smooth function, say infinity, bounded together with all its derivative, defined on Rd times Rd, with value in 0, 1. And it has the following property. Theta of psi1, psi2 is equal to 1. If psi1 is much smaller than psi2, and still psi1 is larger than 1, we are not interested by low frequency, and is equal to 0 if psi1 is larger than 1/2 of psi2, which will be larger than 1. Okay, and then you define TA of B as the following bilinear Fourier multiplier. Theta of psi1, psi2, A hat of psi1, B hat of psi2, d psi2, d psi1. Then you have this proposition. Okay? Firstly, the remarkable fact is that for any function A in L infinity, the paraproduct TA is bounded from H sigma to itself for any sigma in R. Of course, a product by a function which is merely L infinity does not act on H sigma for sigma large enough. But paraproducts are well defined. You can even consider a function with negative order regularity. For example, if you consider a function in H beta for some beta strictly smaller than d over 2, then TA maps H sigma to H sigma plus d over 2 minus d over 2 plus beta for any sigma. What does it mean? You see? You map, let's consider an example. Sigma equals 0. This is L2. And here you have H minus d over 2 plus beta, which is a negative exponent. So you have a function L2, and you map this L2 function to a function with negative regularity, as if this operator contains derivative. So you can give a rigorous meaning to what is the product by a function which is in C minus 1, for instance. It will be an operator for the 1. The key point is that you can replace nonlinear expression by paraproduct or paradifferential expression to the price of error terms which are smoother. For instance, you can compute what is AB minus the paraproduct minus the symmetric paraproduct, and you would get something in H alpha plus beta minus d over 2, provided that A is in H alpha, B is in H beta, and alpha plus beta is positive. This is explicitly in the paper by Jean-Michel Bonny, except that in his paper he's assuming that it is strictly larger than maybe d over 2, and this has been lower just after. Okay? I skip the proof of this proposition. It is in many textbooks, for example, the book by Baouri, Chemin and Danchin, and it is also, I like a lot, in the book by Ormander, his book on linear equation, and he's using a continuous Littlewood Pallet decomposition instead of a dyadic. Okay? No. So with these tools, you complete the proof of the Sobolev estimate for the Dirichlet to Neumann operator. Well, okay. This is the first step. The second step is to improve this analysis by not only proving that it is Sobolev estimate, but proving that it is a pseudo-differential operator. Recall that we have seen that g of 0, we have proved using Fourier transforms that it is the square root of minus Laplacian. I have also said that Calderon was interested in studying the Dirichlet to Neumann operator simply because the Calderon, the so-called Calderon problem, involved Dirichlet to Neumann operator. What Calderon proved is that if eta is a smooth function bounded together with all its derivatives, then g of eta is equal, it's a pseudo-differential operator of order 1. Lambda is a symbol of order 1. The meaning of this theorem is the following. A pseudo-differential operator of order m that we denote by op A of some op of some. This is an operator of the form of the following form. Let's say you consider a function u in the Schwarz class, then op A of u is a function, and at space position x, it is equal to 1 over 2 pi to the d times the integral over rd of exponential of ix dot xi, a of x and xi, u hat of xi, d xi. where A is a smooth function satisfying the following estimate. For any multi-indices alpha, beta, the derivative of the symbol A with respect to x and psi decay with respect to psi as follows. This is smaller than some constant times 1 plus the norm of psi to the power m minus beta. So the more you decay in beta, the more the symbol, the better the estimate. Okay? I will simplify in just 2 minutes the pseudo-differential part and reduce it to only to the notion of Fourier multiplier. So this is why I am not going to give a lot of example or result about pseudo-differential operator. What I need to explain is this result due to David in 2005 that G of eta, in fact, is equal to op of lambda 1 plus r of eta, the following improvement of Calderon result, where lambda 1 is something explicit, lambda 1 is something explicit. This is the square root of 1 plus gradient eta square, psi squared minus gradient of eta dot psi squared. And r of eta is an operator of order 0. What does it mean? It means that it maps h sigma to h sigma, assuming that eta is in h sigma plus k, where k is a constant depending only on the dimension, which is larger than 1, if you look at the proof. Okay? So now what is the big simplification that I am going to make? The running simplification. The running simplification is that d equal 1 implies what happens when d equal 1. When d equal 1, this scalar product is a product. So this term cancels with this one. So lambda 1 is simply the absolute value of psi. And op of lambda 1 is equal to modulus of dx. So in dimension 1, there is no need to know the definition of a pseudo-differential operator. It's simply a Fourier multiplier. The first important remark, and remark number 2, k, the number here, this corresponds to a loss of derivatives. Why is that? And this is some important remark. We have a domain, a fluid domain of this form, and we want to understand the Dirichlet to Neumann operator. So we have a function psi defined here on the free surface, it will give rise to an harmonic function phi inside the domain. And then we are going to go from the harmonic function to the surface by considering the trace of the normal derivative. This is to understand the Dirichlet to Neumann operator means to understand this operator. Okay? For the purpose of having a figure which is easy to follow, I plot it like a kind of analytic function. But we are studying function with finite regularity. Okay? Let's say close to be Lipschitz, close to be a cusp. And we are not going to think of singularities by means of edges and so on. We think, like Fourier did, of singularities in terms of frequencies. Okay? Small scale correspond to high frequencies. Okay? So we have to imagine that our domain is of that form, highly oscillating. Psi itself contains oscillation. Phi will contain oscillation. And this becomes a mess, because in phi, you will find oscillations that come from psi, and also oscillations that come from eta. And you have to decouple this. One way to decouple this is to assume that eta is much smoother than psi. Because, let's say, you know that eta is much smoother than psi. And you want to make a picture. Much smoother means that it oscillates much slower. So essentially, eta does not oscillate, psi oscillates. So essentially, you are exactly in the situation of the Fourier transform. And this is the content of a Calderon result. Calderon result tells you that if eta is smooth, okay, you can really conjugate your equation. You can really conjugate your equation to straighten it to the half space. Okay, you can deform your equation, you straighten it, it's enough. Now you can still do this game, assuming only some kind of optimal loss of derivative. But for us, this loss of derivative to study the Cauchy problem is not good, because eta and psi have exactly the same regularity for the water wave system, because the two equations are coupled. So we need to uncouple this. And this is where we need a further computation that we did with Guy-Métivier. With Guy-Métivier, we computed the remainder term R of eta more carefully. And for that, we used Boni paradifferential operators, and not only paraproducts, and also Alinac paracomposition operators. Okay. By so doing, what is the result? So this is with Guy-Métivier. Still d equal 1 to simplify notation. So recall the notation. Capital V is dx phi evaluated on the free surface. Capital B is dy phi. Then you can write g of eta psi as mod d of psi minus tb eta minus dx of tv eta plus some remainder term f where f satisfies the following estimates. Let's say minus 4. Provided that, say, gamma is larger than 4 and S is larger than gamma. We have several estimates. Anyway. So you can compute exactly what is R without loss of derivative up to doubling the regularity. Another way another approach which has to do with the quasi-linearization approach that I mentioned on the first lecture will be to prove the following estimates. Still in dimension 1 to simplify notations. You give 1 epsilon of room, and you consider an index sigma in 1 half and then S minus half. Okay? Then R of eta maps H sigma to H sigma minus 1 plus epsilon in terms of the Sobolev norm of eta. So there are two alternative ways to compute what is the remainder term that you would get by following the proof of Calderon and David Lann. What is the idea of the proof? The idea of the proof, again, we work with the function obtained by flattening the domain. And as we have seen, it satisfies a PDE. It satisfies the PDE, and the coefficient alpha, beta, and gamma are equal to 1 plus eta x squared. Beta is minus 2 eta x, and gamma is eta xx. Then the idea is to paralinearize. Paralinearize just means replace products by paraproducts. I just replace the usual products by paraproducts. What is the price to pay? I have to take into account the remainder term and also the symmetric term. T of something acting on alpha, T of this quantity acting on beta, and also, for example, there is in F the term T of dZV acting on gamma, which is eta xx. So, for example, on the right-hand side, I have this term. This term, this is a paraproduct acting on some function. A paraproduct is never a smoothing operator. You never smooth a function by multiplying it by something. So it's at most of the regularity of this term. At most. So at most, twice derivative less than eta. And indeed, this will be the case. This is indeed a function which is continuous in Z with value in H S minus 2, provided that eta is in HS. So this is not optimal. The optimal thing to do will be not to consider a change of variable. The good idea is to consider a para-change of variable. The main difficulty is that there are very few people who know what is a para-change of variable, because my former colleague Serge Alinac from Orsay wrote his article in a way which is a kind of cryptic. Okay? And Neumann recently he wrote the paper in a way that you can learn the theory. So easy to handle para-change of variable. But there is an essential result of Alinac that tells you that a para-change of variable, instead of considering a change of variable, consider a para-change of variable, key star, will satisfy this result. This is equal to the usual change of variable minus T of phi prime composed with chi, acting on chi, plus some good remainder. So what we did with Guillemetivier is this very small trick. If it is the main result that characterizes para-change of variable, you simply consider that this is the definition of a para-change of variable. Because to define this, it's enough to know the definition of a paraproduct, which is easy. So you consider this transformation. What does it mean? There is a function phi. This is a differential. To clarify the notation, this is just the function u. Instead of working with the function v that you get by flattening the domain, you say u is equal to v minus t of dzv acting on eta. Okay? This is So the lemma is this quantity satisfies the previous equation. Okay, as V does. But now the source term is much better. It is continuous in Z with value in H2. It's important. 2, you double the regularity, minus a constant depending only on the dimension, which is 5 plus D over 2. Okay, but for us, D equal 1, so this is minus 3. Okay. What is the proof of this lemma? Okay, you take your equation, you paralinearize, you keep all the term, you have all the term, and you track the cancellation. You have a lot of trouble term, but you know in advance that the sum of all the trouble terms should vanish, and it happens in the end. It remains only the remainder term for Boni paraproducts, for which you know that you can double the regularity. And you have some loss because you have some derivative acting on this remainder terms. So you have this equation. Now, to conclude the proof, of the proof is not very difficult, but I skip it simply because I don't want to define paradifferential operators. But I can explain the philosophy of the proof, which is simple. It is in 2 steps. Elliptic factorization. Elliptic factorization, what does it mean? Here, you have an operator. Write this as P acting on U. You seek 2 symbols, A and capital A, such that P is equal to T alpha composed with dz minus TA, dz minus T capital A. You have an operator of order 2 that you factor out as the product of 2 operators of order 1. The important point is that this is a computation that you can do in a systematic way. You don't need any trick. You just write, I want A, I want capital A, such that I have this. Then there is something called symbolic calculus for paradifferential operators that tell you, well, then TA composed with T capital A is equal to this, and so on. This gives you a cascade of equations that you solve. Okay? And you can do that. And the second step, it's elliptic regularity. You set, here you have 2 symbols. One with real part smaller than C times capital absolute value of psi, and real part larger than C times absolute value of psi. You introduce W, which is dz minus T capital A acting on U. Then you have an equation for W. This is dz of W minus TA of W is equal to some source term which is OK. And you see this equation, let's say, okay, the model equation is this one, the real part being this. The model equation is this one. That is dz of w plus modulus of dw is equal to some source term which is OK. And you have to see this as an evolution equation. You have your domain that has been flattened, and you have two directions, from the top to minus infinity, and from minus infinity to the top. And this is an equation from minus infinity to the top. It has a source term here that is smooth. It has an initial data at minus infinity, which is 0. You can propagate the regularity and get that W on 0, which is the finite time, as the regularity of F, that is, it belongs to H2S minus something. If you don't want to go down to minus infinity, you can truncate. Whatever you generate in the bulk is not an issue because it will be smooth. From the time it goes to minus infinity to the surface, it will be smooth as if it was smooth by the Poisson kernel. So W of 0 is smooth, but W of 0, what is it? It is dz of u minus t capital A of u. So this gives you a paradifferential expression of dzu, that is a normal derivative of u in terms of tangential derivative, and it is exactly the meaning of this result. Once you have this, well, once you have this, you can almost, I will finish with this. What you can do, you can give a rigorous meaning to essentially some computation in the first paper by Zakharov that I mentioned. Okay? You have the Zakharov system, Craig-Sulem Zakharov system, starting with dt of eta is equal to g of eta psi. You replace g of eta psi by this. So you introduce a notation, let's say omega, for what we call with Guy Métivier the good and noun of Alinac. Good and noun of Serge Alinac. You replace the equation dt of eta equal to g of eta psi by dt of eta equal to modulus of d omega minus dx tv of eta plus some error term f1 of eta psi. There is also an equation for psi, and it is much easier to paralinearize it. It's just the paralinearization of products. If you do so, what is nice is that you obtain an equation of that form. dt of omega plus tv dx of omega plus ta of eta is equal to f2, where a is the Taylor coefficient, a is positive. This is the proof by David that we already mentioned. Then, as we have already, okay, you symmetrize your system of equation. You symmetrize your system of equation. Let's say you look carefully. You have a modulus of dx acting on the first equation, ta acting on the second equation. So the good choice is to consider capital U which is paraproduct by the square root of A, well defined because it's positive, mod D to the 1/2 omega. Okay?
Can you recall what is A in your system?
Yes. A is minus dyp on the surface. And if you don't like to have some function which is not defined, P, there is a formula. A is equal to 1 upon 1 plus gradient theta squared times G minus G of eta acting on eta plus, plus V G of eta V plus B G of eta B minus G of eta 1/2 of V squared plus B squared. And recall that V and B can be expressed only in terms of eta and psi, so this is a closed system. And the fact that it is positive convexity property that goes back to this computation by Stampakia, okay, that you can perform a convex change of a noun for elliptic equations. Well, so for this unknown, and not for eta and psi, you have a system of the form dtu plus some matrix D acting on U plus some quadratic expression plus some cubic expression is equal to 0. I'm cheating a bit to save time. I don't like to. Q is a quadratic expression of order 1. C is a cubic expression and in fact there are terms of higher orders. Okay?
Why it is D and not modulus of D?
Thank you. And D is a matrix we have a system, a 2x2 system. It's a notation for this matrix. A bad notation because it's neither diagonal nor for the one.
Yes, it's like,
okay, and what Zakharov did in his first paper?
it's like taking a variable.
No.
No?
It's not symplectic. Zakharov is symplectic,
Okay.
but this is not.
Even if its matrix is perfectly...
But this transformation is not symplectic.
Okay.
I mean this transformation, sorry. Okay? What Zakharov did in his first paper, he said, well, by a normal form transformation, we can remove quadratic term from the equation and get only cubic term. Okay? We can remove quadratic term and get only cubic term, which is much better because Zakharov is interested by the stability of small solution, which is already a very delicate problem. So cubic terms are much better than quadratic because they are smaller, obviously. So Zakharov says we can remove quadratic term. No, we cannot, because it's a quasi-linear problem. It's losing one derivative. The flow is not C1 as Neumann proved. You cannot remove quadratic term by a transformation which is bounded on Sobolev spaces. Zakharov didn't care, and he's probably right to do it. But for the purpose of proving a theorem, you cannot. What you can do is this. There is a statement, for instance, I conclude with this, a rigorous meaning to what Zakharov did in his first paper in 1968. There exists a parameter gamma and a transformation and a transformation, a nonlinear change of unknown satisfying that this transformation is of order 0, bounded on Sobolev space, this transformation is of order 0, a perturbation of the identity, quadratic, bounded on Sobolev space, such that if you consider, this is a bad notation. Okay, anyway. If you consider the effect of this transformation, okay, you perform the transformation, nonlinear change of unknown, and you commute derivative with the equation, because you want to prove Sobolev estimate, you commute derivatives. What do you get? You get an equation for phi dot of the form dt of phi dot plus d of phi dot plus lu of phi dot plus c of u acting on phi dot, the terms, is equal to gamma, where gamma is a source term gamma is a cubic source term, well estimated in L2, and this is a cubic term, so it's okay. And you still have a quadratic term, but it disappears from energy estimates. Okay, so what we prove with Jean-Marc is this result. You cannot remove quadratic term by a transformation which is bounded on Sobolev space. But you have the flexibility to add, we are not removing, we add a term to the equation, the effect of which is to cancel the original term. It's easy to understand. Let's say you have dt plus v dx. And I try to remove v dx, which is delicate because you want to remove an operator for the 1. What you can do is, in fact, to add. Okay? Let's say you are going to add the multiplication by 1/2 of dxvf. Why is that? Because now this term is antisymmetric on L2. So as if it disappears, it vanishes from L2 energy estimates. And so it's enough to add a term which is of order 0. So this is what we did. Okay, and I will stop here. Thank you very much for your attention. I will put the lecture note of my web page if you or on Thierry.
On the summer school's web page.
Okay. Thank you.